Now what we're gonna do now, we're really ahead of the labs, very far ahead of the labs, but in summer, the labs in the class become a little bit disjointed because we just gotta keep moving. In the first semester, we learned about position, which is measured in meters and typified by either X or Y. We have velocity, which is V, which is dx, dt, or in meters per second. We know about acceleration, where A is dv dt, so it's meters per second squared. And we've been playing with this for the last week. We're going to introduce some new ideas, and the first of which is if you take, we've done this, mass m kilograms, and we've done force. If you take mass and put it together with acceleration, you get a force. Object in motion stays in motion unless you F with it, and the F is the force. The force is measured in kilograms, meters per second squared, or it could be even a Newton. And so really what I'm doing is I'm just kind of reviewing the last week of material. But now we need to move on top of it. We need to do something, and sadly it's not going to show up on the screen. But what we have here is just a simple eraser, and I'm going to do this to it. Just let it go and let it fall. And we've studied that in one-dimensional motion. It falls with a rate of -10 meters per second, etc. But there's also something that we need to do. There's a difference. Make it a little bit more dramatic. So let's say I take this chair, and I know you can handle it because you're not going to think I'm actually going to do this. So I take this chair and I hold it above you. Now I've got your attention. So if I drop it, that's going to hurt. What are some ways that I could make there's only two quantities that I'm really going to change in this. How would I make that chair hurt more if I dropped it? Add what? Add force. Well, I mean, yeah, that, but I'm looking for something a little bit more simple than that. I can either A, drop it from a higher position, or B, go get a bigger chair. So there are some things that we need to think about where it has the potential to do ouch to something. You can either drop it from a higher point or get a bigger chair. And so the things that I'm talking about is the concept of potential energy. That when you have an object that is suspended above you, it has the potential to end up at your location with a particular speed. And we're going to go into that relationship. Potential energy, and more to the point, gravitational potential energy. Well, we got to introduce the idea of
work. Work, which is typically W, is force times distance. If I apply a force for a particular distance, then I've done a certain amount of work or energy into the system. If I have this calculator and I lift it up from there to there, what was the force that I overcame? Gravity force. Well, what's gravity force? mg. Well, force times distance, that distance is d. So if you have an object that is lifted up and you're overcoming a force F, the work or the energy needed or mgd. Now typically I use h as the height, so we word associate with that. So potential energy, which is gravitational, is mgh. So if I lift this 1 meter up, let's say I put 10 joules, well actually that's a great question, units of energy. Now, when you look at the units, work is a unit of energy, potential energy is also a unit of energy, F, mg, both force. So the units of energy could either be kilograms, meters, second squared times meters, m, g, h, those are the units. So you could express this as either a Newton meter, or you could express it as a kilogram meter squared second squared, or more simply, you can express it as a joule. So the joule is the unit of energy. So if I put 10 joules of energy in lifting this calculator up a particular distance, and I let go, I'm going to get those 10 joules back. Now, this is all currently assuming conservation, and I'm going to start using this term correctly, conservation of mechanical energy. In the conservation of mechanical energy, or as a lot of people just say, conservation of energy, that your initial energy is equal to your final energy if there is no friction. So if there's no friction in a system, yay, no friction, you know for a fact that your initial energy is going to be the same as your final energy. So let's put this in perspective. So a 5 kilogram object falls from a height of 10 meters. What is its potential energy at the beginning, or PEI, and how much energy is left when it's about to hit the ground. So all I want to know is how much potential energy is at the beginning and what's the energy in the system as it's left. So initially, and it's going to be dropped, and at the bottom, right when it's about to hit, it has a particular amount of energy. This potential energy here is just mgh. So it is 5 times 10 times 10, or 500 joules. So it has an initial potential energy of 500 joules. Well, at the bottom, its final energy is still 500 joules. There was no friction. It's a lot like, so I have, actually I'll use those whiteboard markers. So in terms of the conservation of energy, you can think of energy as these whiteboard markers. I'm only going to use 5, and then these markers I'm going to deny their existence. So I've got 5 whiteboard markers in the room. Okay? So how many whiteboard markers are in the room? 5. Well, I'm going to put one down right there. So how many whiteboard markers are in the room now? 5. Well, what if I take another one and I put it here, and then I take another one and I put it there? How many whiteboard markers are in the room? 5. So if there is no friction, the energy that you have at the beginning is the same as the energy that you have during the motion, and the same as the energy that you have at the end of the motion. The only way that this number could change is if I took a whiteboard marker and just chucked it out the room. That particular marker is now out of the room, which means that friction has removed energy from the system, and so we have fewer markers to play with. The other thing that I want to get is, or take a look at, so I have a whiteboard marker, the red marker and the black marker. Which one has the higher potential energy? The black marker. Why? It's a higher. Now that's assuming that they have the same mass, but they do. So the one that has a higher elevation has the greater potential energy. Now, what's really interesting, here's another question. If these two start at the same level, and then this is the motion, do they have different potential energies from each other, or do they have the same potential energies as each other? They have the same. All that matters is the height. The fact that one went straight up and the other one went at a particular angle doesn't change the fact that they both start at the same elevation and they finish at the same elevation. So now, working with the whole idea of if I look goofy in front of the class remembers it. So if I start here and I move it over there, what was the change in potential energy? Nothing. What if I do this? Starting and ending elevations are the same. Did it change its potential energy? No. You don't particularly care about what it's doing in the middle. All you care about is the state at the beginning and the state at the end. So now this is the dramatic, goofy part. If I start here and then do, and then beginning and ending elevations are still the same, what's the change in potential energy? None. So it doesn't matter if it's complex, goofy, or dumb. If the beginning potential energy elevation is the same as the end elevation, there is no change in potential energy. That's what you need to remember. So we've shown gravitational potential energy. The next thing we're going to talk about is kinetic energy. Kinetic energy, energy of motion, kinetic, motion. Potential energy, energy to do stuff. It has the potential of doing stuff. Now, I'll have to, throwing a chair into the audience won't work well. Oh, I can use this. I don't need a demo room, I got stuff on this desk. So, kinetic energy is energy of motion. So if I took this thing and I just chucked it in your face, it would hurt. And it wouldn't be something that I would drop, it would be something that I caused a motion and did that. So what are the two different ways that I could do to get this to hurt the student more? More mass, get a bigger tape dispenser, or what else? Throw it harder, increase its velocity. So if I threw this at you faster, it would hurt more. If I got a bigger tape dispenser, I got one in my office, I can go get it if you want. If I threw a bigger object, or I threw it faster, it would hurt more. Now, this relationship is 1/2 mv squared. That the kinetic energy of the object is 1/2 times its mass times its velocity squared. And what's really interesting is if you double V, kinetic energy quadruples. One of the reasons why, I understand you guys are 18 to 22 or a little bit older, you've got all your life together or ahead of you, you're invincible, but don't speed. If you, let's say, this is one of the things where if you're traveling 30 miles an hour and you hit something versus hitting something at 60 miles an hour, you've got 4 times the energy that you had at 30. Let's say, compare, I don't know the meters per second offhand, but compare the kinetic energy of 60 meters per second divided by the kinetic energy at 30 meters per second for an object that's moving at those velocities. So one is moving at 60 meters per second, the other one is moving at 30 meters per second, and compare those. And one of the things that you can say is, well, I know kinetic energy has mass. You didn't give us mass. And I say, yes, I know. Which means, in this particular problem, you don't need it. The kinetic energy at 60 is 1/2 mv60 squared. The kinetic energy at 30 is 1/2 mv30 squared. M's cancel, halves cancel, and I'm left with 60 squared over 30 squared. And that gives you what did I go for? Oh, 30. And that gives you 4. So you have 4 times the amount of kinetic energy. If you triple the velocity, it's 9 times. If you quadruple the velocity, it's 16 times. That's why car crashes at high velocity are quite exciting because they have all that energy in that moving object, and when something hits the wall, that energy goes out somehow. Another example, NASCAR cars or Indianapolis or Indy cars or any type of racing vehicle. What's the one thing that you notice when those cars slam up against a wall? They basically disintegrate. Stuff just goes flying everywhere. It's really exciting when the tires fly into the crowd. But why is that? Because what they want to do is they want to get that energy of all the parts of the car away from the most important part of the car, the driver. So when the NASCAR slams into the wall, the engine separates, the wheels go flying, it just vaporizes, except for the car cage that's holding the driver. And so I understand you want to get to the bar faster or whatever you need to go, but if you there's a reason why we have speed limits. The faster you go, the more energy that you have available to you that could end up doing things like shred your body, kill your friends, stuff like that. Hate to sound like an adult, but just behave and everything will be fine. And this is the math that shows it. So if in the first part, I drop this object from 10 meters high, I want to know the velocity at the bottom. So dropping what is the velocity at the bottom? What is the final velocity? We could do this one of two different ways. We could do it the way that we've learned in the last week. With motion, we know that our one-dimensional motion equation says, and we're going to go down in this particular case, I'm going to set the origin here. That is 10. The initial velocity is 0. And so I need x equals x naught plus v naught t plus 1/2 at squared. That's 0, that's 0. Solve for t. 2x over a is equal to t squared, or the square root of 2x over a is equal to t. So I've got that. So 2 times 10 over 10 square root is 1.41 or something. 414 seconds. And if I know it's been dropping for 1.414 seconds, I know that the final velocity is v naught plus at. So this makes it 10 times 1.414, which is equal to 14.14 meters per second. And so that's the final velocity, and it's a simple way that you can do this. There's a reason why I call those motion equations my first and second favorite equation, because they allow you to do such cool stuff with motion of particles, ballistics, throwing a baseball, hitting a baseball over the right field wall, all sorts of interesting things. A close competitor to my two favorite equations were the energy equations. And why is that? Because in dropping the object, all I have to know is what's the energy at the beginning and what's the energy at the end. And I can figure out all sorts of things. My initial energy is the potential energy, mgh. My final energy, my kinetic energy, is 1/2 mv squared. So the m's cancel. One of the things that you can look at this, and we'll start throwing these words around, It is mass independent. You could drop an elephant or the mouse, and if it falls 10 meters, it's going to have a particular velocity. Solving for V. 2gh is equal to v squared. So the square root of 2 GH is equal to V. So this is equal to 2 times 10 times 10, or the square root of 200, or once again 14.14 meters per second. So this is a very simple way of introducing conservation of energy. If you know it's energy at the beginning, what do I know? Let's ask a few questions, and it's really, we should fill in something here. That initial energy and energy final, if we're to do this a little bit more OCD-ish and thorough, I would really write it like this. Because there will be situations where you do have to know all these variants. So that last line is kind of the general way of expressing the energy and emotion. What do I know about the energy initially? Is it moving? Class? Is the object initially moving? No. So if it's not moving initially, its kinetic energy is 0. So there is no kinetic energy. So typically when you hear that word drop, that means that the initial velocity is 0. At the bottom, its final state, which is 0, potential or kinetic? Potential, because it's at the bottom of, it can't go any further down. So its potential energy is 0. And so being able to identify the states, where are the whiteboard markers in the room, where is the energy in this particular state, you'll be able to identify where all this is and figure stuff out. This is the reason why probably this was my first choice for my favorite equations, but if it couldn't fulfill the obligations of being my favorite equation, this one was going to step up. Energy equations are very good They're very good at finding the final velocity very quickly. If I was given a physics problem and I was told to find the final velocity of the object, I would use energy. Bam, just get it done. If I needed to work with position, then I would use the equations of motion. The equations of energy just work so darn fast. Now, when I told you about gravity potential energy, I initially said potential energy and then I clarified it. There is another form There's another form of potential energy, and that is PE sub S, which is spring potential energy. The potential energy coming from a spring. We've all seen springs. If you take a spring and you compress it, what's the thing that you notice? It pushes out. If you take a spring and you pull it out, what do you notice? It pulls it back in. Springs use Hooke's law. Hooke's law describes the force of a spring on whatever's pulling it apart or compressing it. If we have a wall and we have a spring like this, and this is the unstretched position. So in this particular case, the X will be 0. So if the spring is just sitting there doing nothing, the end of the spring is at its unstretched position. And the force that that spring gives is 0. If I stretch it, so if I pull it out here by a distance x, there will be a force pulling on it in the opposite direction. If I compress it, then the X is in that direction and the force is in the opposite direction. So no matter which direction X is, the force on the spring will always be opposite that of the displacement. So X we'll call displacement, and F is the force. Hooke's law, using vectors, we write it as F equals negative kx vector. That the direction and magnitude of the force from the spring is equal to the negative value of something called k times its displacement vector x. So if x is to the right and you got a negative sign, then F should be to the left. If x is to the left, you got the negative sign, so F is now to the right. How I typically use it, I use typically the in magnitude, F is equal to kx, and then I just worry about, I know logically if you're pulling the spring, it should be pushing back, all sorts of things that these two, as far as I'm concerned, are equivalent. This one is the formal, this is what I typically use in problems. I drop the negative sign and then I just let logic dictate the directions. Now, what is K? K is the spring constant. That's what you call it. Now, the units, a lot of times you sit there and go, well, I don't know what the units are. And then I ask, well, what is Hooke's law? Well, Hooke's law is F equals kx. So and then I would say, well, solve for K. Okay, K is F over X. So now that you have K as a value of F over X, what are the units of force? Well, that's a Newton. And what are the units of x? That's a meter. So the units of a spring constant can be easily determined. K is equal to newtons over meter, newtons per meter. That is the spring constant. As an example, we could, we have a spring in an unstretched position and it's hanging, so we have gravity pulling down. And I put a 5 kilogram object on it, and then I slowly lower it until it reaches a new equilibrium point, and it has stretched a distance of 10 centimeters. So what I did is I took this spring that's just hanging from the ceiling, I attached a 5 kilogram mass to it, and then I slowly lowered my hand until finally the mass lifts up out of my hand. The question is, what is K? So that's going to be the quick question that we have to ask. Well, how I would do it is say, well, what is this thing doing? Well, I've said that the velocity is equal to 0. I said, excellent, that's all I need to know. Because if I know it's not moving, what do I know for a fact? I could know potential energy, that's not what I'm looking for. In terms of motion, and then what are the implications of that motion? Cricket, cricket, cricket. Is it moving? No. So if it's not moving, it must be in blank blank. I'm going to get to you, but I got to deal with her first. First, your answer was horribly wrong. Second, what saves you is the fact that you said it with confidence. And I do appreciate that. You just said static friction. It could have been green elephant. And I would have been like, okay, that's good. Very good. I'd rather have you say something wrong than just sit there, think the right answer, and just not tell anybody. You said equilibrium. Yes, you are correct. It's in translational equilibrium. And if it's in translational equilibrium, that the sum of the forces in this direction, which we typically think of as just y, is 0. Much like observation of a book resting on a table, that the normal force balances out gravity force. But in this case, it's not normal force that is balancing it out. You have the force of gravity pulling down, but you have the force from the spring pulling up. And those forces balance, because you know if its velocity is 0 and it stays 0, you know that acceleration is 0. If you know that acceleration is 0, you know that the sum of the forces, because sum of the forces is equal to ma, if A is 0, then the sum is 0. And so that's why I get to write this. In this particular case, this is one of the reasons why I just use the magnitude. If this object is hanging down, I know that gravity is pulling this mass down, so I just go minus mg. But I also know for a fact that this spring is pulling up. So I just write positive kx. Now Hooke's law says negative, but I don't want to deal with all that negative of a negative where the displacement is negative and It just bothers me. But I know for a fact that that force has to be up. I've set my number line or my axis that up is positive. So I'm just gonna give it a positive and not worry, not sweat all that logic that has to go into it. So mg is equal to kx, or k is equal to mg over x. Now m is 5, g is 10. The x value, what number do I put in for x? 10? Okay, you said it with confidence, but you're wrong. What is the, and this is an important part of the matter. What value did I give you? What are the units of the displacement? It's in centimeters, so you have to convert it to meters. So 0.1. So that means 500. When you do conversions, or when you do any physics, be sure all of your units are converted into kilograms, meters, and seconds, unless I specifically say, give it to me in some other form. You can never go wrong to converting your masses to kilograms, your distances to meters, and your time to seconds. Because a Newton is a kilogram meter per second per second. A joule is a Newton meter. Everything that we're doing is based on those three units: kilograms, meters, and seconds. Now let's do this. Let's take this spring and put it on our experiment table. And what we're gonna do is, with a K of 500 newtons per meter, we're going to compress it 0.3 meters. Now it's on a frictionless table, yay, no friction. What I want to know is, what is the velocity of the mass as the object or as the spring reaches its equilibrium point? This is similar to just taking an object and dropping it. What we've done is the energy initial is equal to the energy final. What is the initial position? The initial position is its compressed position. What is its final position? Its final position is its uncompressed position. It's the moment at which the mass is released from the spring. Initially, there is no kinetic energy. So the initial energy is simply, and this is, finally I get to use this, the potential energy of a spring is 1/2 kx squared. So we do 1/2 kx squared. We'll use the same mass, 5 kilograms. The energy final is all kinetic, so 1/2 mv squared. So the initial energy, all potential energy of the spring, the final energy is all kinetic. Those cancel. I'm left with kx squared over m is equal to v squared. So x, k over m is equal to v. So plugging in our values, x 0.3 square root of 500 divided by 5. Oh, I love the numbers. I must be subconsciously working this through. 500 divided by 5 is 100. 100 square rooted is 10. 10 times 0.3 is 3. So the answer is 3 meters per second. I worked really hard to make sure that Atwood's machine problem just cranked out an acceleration of 4 was the answer for the Atwood's machine acceleration. 4, not 4.0221, 4. So the answer coming out is 3, so 3 meters per second. All of the energy has been converted from spring potential energy to kinetic energy. Well, let's start making things a little bit more complex. Let's add, you have a spring where we'll use the same mass equals 5 kilograms. The K is equal to 500 newtons per meter. And the compression distance, X, is 0.3. There is a hill. The height is 20 meters. And I want to know the velocity at the bottom of the hill. Major question, is there friction? No. Yay, no friction. If there is no friction, the next question that I asked, or the next questions that I ask are, where does it start? And where does it finish? Its starting position is top of the hill and compressed. The bottom of the hill is its final position. In this particular case, now we have 2 potential energies that we have to consider. The potential energy of the compression of the spring, the fact that it's on a hill, are all the beginning potential energies that I have to deal with. So its initial potential energy is potential energy of gravity and potential energy of the spring. It's not moving, so there is no kinetic energy. The final is the kinetic energy final. It's at the bottom of the hill. It's uncompressed spring, so there's nothing left in terms of potential energy. So you figure this out. Potential energy of gravity, mgh. Potential energy of the spring, 1/2 kx squared. Kinetic energy, 1/2 mv squared. Multiply by 2 and divide by m. So it is 2gh plus k over m x squared is equal to v squared. So I multiplied by 2 over m is what I did. And then I take the square root. So v is equal to square root of 2gh k over m x squared. And so now we plug and chug. Ah, not you. I want you. $20.2. And so that is a combination energy problem. The biggest thing about figuring out energy is detail or understanding what is going on at the beginning and understanding what is going on at the end. Much like when I looked so goofy by moving the thing over and over again. All you cared about is what is it doing at the start and what is it doing at the end. What it's doing in the middle, I don't particularly care. Now, what does have to be considered about the middle is when we answer the idea of, or add the idea of friction. Boo, friction. So when you're adding friction into the mix, the initial energy is not equal to the final energy. With no friction, the energy initial is equal to the energy final. So you could say that energy final over energy initial is equal to 1. So if there is no friction, that ratio is 1. If there is friction in it, the energy final over energy initial should be less than 1, or energy initial over energy final should be greater than 1. Or I'm sorry, not 0, 1. So with no friction, it's 1. Adding friction, you get ratios that are different from 1. With no friction, you get this. With friction, you get this. Now, the way that I write it, I think, is a little bit different from the book. But I write it like this. The energy initial minus the energy removed through friction is the final energy that you have. I like to think of it as the checking account equation. The money that you have at the end of the day is equal to the money that you have at the beginning of the day minus the money that you spent. So we need to determine how much energy friction spends. Now, how does this friction work? When you, perfect example would be just to simply take your hand and rub it across the table. So what's happening at a microscopic level? The surface of, you know that question?
No, I have a question.
Yeah.
Is that a W?
Yes. It's a mutant W, thank you. So when you take your hand and rub it across the table, little bits of the table are coming into contact with your hand and they're catching and they're ripping apart, and what ends up happening is that heat is released. So if you sit there and you rub your hand long enough, well, in addition to getting a splinter, but what happens eventually is the surface becomes warm. That energy from the motion of your hand is being converted into energy through friction. The friction is like the equivalent of taking the whiteboard marker and throwing it out the room. We calculate this energy through the following. The work is force times distance. So if we have the force, well, what force are we overcoming through the motion of this object from side to side? It's the friction force. The friction force times distance is the work removed through friction. Say, for example, we have an object and it's moving to the right. Well, we know that there's a force of gravity down, there is a normal force to the right or above, and then there's a friction force to the left. Those are the forces that act on it. And so when it gets over here, it has traveled a distance d. So the work removed, or the energy removed through friction, is just the friction force times that distance. Now the way that let's just do it. Sum of the forces in the vertical is equal to 0. I know that the object is not penetrating the surface or flying off. So this becomes normal force minus the gravity force. So normal force is equal to the gravity force, which is equal to mg. The friction force is mu sub k times normal force. So this is mu sub k mg. Which means that the work removed through friction is mu sub k mgd. Because the work is equal to the friction force times the distance. So let's say we have an object moving with a velocity of 50 meters per second, and it's traveling across a frictional surface where its mu sub k is 0.1. What I want to know is, what is this distance d when the final velocity is 0? Effectively, what we're doing is we're taking all that kinetic energy that we had at the beginning, releasing it through friction, and until there's nothing left when it comes to a stop. So writing our just general checking account equation, we have energy initial minus the work is equal to energy final. I told you at the end of this specific problem that it wasn't moving, so there is no kinetic energy. I don't have to worry about potential energy because of two things. One is there's no springs, and two is there's no change in height. Technically, there is a potential energy over there, and there is a potential energy over here. But those two potential energies are the same. The heights are the same, so I don't worry about it. If the object remains at the same level, you don't have to bother with it. The energy initial is all kinetic energy, so it is 1/2 mv squared. The work removed through friction, mu sub k mgd, and that is equal to 0. 1/2 mv squared is equal to mu sub k mgd. Those m's cancel. I'm given velocity, I'm looking for distance, so this is v squared over 2 mu sub k g, and that is d. So this becomes 50 squared over 2, 0.1 times 10. That effectively cancels, and it's 2,500, I think it's 1,250. Yeah, so it's 1,250 meters. So you're able to figure out how far this thing goes by its initial velocity, the friction. If you're able to study it generally, this is a core equation for just an object sliding across a frictional surface. So you'd now be able to solve for gravity, distance, velocity, and the coefficient of friction. So you could solve for any of that. So no matter what I ask for, you can have it. All right. The next thing that I need to introduce is we have the idea of energy. And now I have to introduce the idea of momentum. Energy and momentum are an odd little pairing. Momentum well, energy, the typical, we're just going to look at kinetic energy in this particular case, is 1/2 mv squared. Momentum, P, is equal to mv. Now, it's an odd thing. Why use P for momentum? Well, first of all, mass is already taken care of that little m. P is actually used because momentum in Latin is called impetus, or it's all related to impulse. So the P comes from there. The units of momentum are simple. It's just kilograms meters per second. There's no fancy schmancy word for it. It's just kilograms meters per second. Unlike energy, which is joules or Newton meter or kilograms meters squared per second squared. Now, momentum, if you have an object and it is moving, so a 20 kilogram object is moving at 5 meters per second, its kinetic energy is 1/2 20 5 squared. 20 divided by 2 is 10. 10 times 25 is 250 joules. Its momentum is 20 times 5, or 100 kilograms meters per second. And so you get its momentum and kinetic energy just by plugging in that stuff. The reason why momentum is so handy is because it is so useful in terms of working with collisions. Collisions, as in 2 cars smashing into each other, a boxer hitting another boxer, anything where there is 2 objects that are moving and then they come together and then they interact. Collisions there are 2 types of collisions. One is elastic. The other one is inelastic. In an elastic collision, what are the things about this? Elastic collisions, energy is conserved, or we could say mechanical energy. The other thing that we can say is that momentum is conserved. That's the conservation of energy, that's the conservation of momentum. Elastic collisions are rare. I've only heard of a few instances where it was a legitimate elastic collision. The thing about elastic collisions is, in terms of your bottom line, are multiple choice. Yes, I will ask questions about elastic collisions on multiple choice. On problems, no. You will not get an elastic collision on the test. I think I've eliminated it from the problem set. Elastic collisions, it used to be, let me make sure. Yeah, you got all inelastic. So the thing about elastic collisions is that if you were to set up an elastic collision problem, it's a very It's a very meticulous problem. It requires just sitting there and working with a lot of equations. And so I typically assign one elastic collision problem just to show you how much you hate it and for you to appreciate that it's not going to be on the test. But because of limited time, we're not going to do an elastic collision problem. Trust me, you don't want that. So then we do inelastic. Now inelastic, whereas this is rare, inelastic collisions are quite common. They're everywhere. In an inelastic collision, momentum is conserved, but energy is not. And so would you get it on a multiple choice? Yes. Will you get a problem on it? Certainly. Now it may be that if you, I haven't even thought about test 2 yet, but an inelastic collision problem is very legit. What are the giveaways for an inelastic collision? If you see the word stick, if you see something change shape, stuff like this. And typically the inelastic collisions go something like, you have 2 hunks of cookie dough, one moving at a particular velocity and the other one sitting still. They collide and stick. That's an inelastic collision. If you see an inelastic collision problem, energy is lost through reshaping. When those 2 cookie dough balls collide, they change shape. It requires energy to change the shape of an object. So that's where some of the energy goes. There is a little bit of heat released. Those 2 objects slide across, parts of it slide across the other. That's friction. Friction releases heat. Heat is energy, and so that's where some of the energy goes. And sound. It requires energy to create a sound. So when that sound is created, a little bit of the energy of the system goes away. And so that's why energy is not conserved. If you, on a test, for a problem, for an inelastic collision, if you start saying that energy is conserved, I will start to nervously twitch. I will know about it. And I will say, someone in the room is conserving energy in a collision. So don't do it. A simple example. You have an object moving to the left and its speed, I'm drawing it this way, its speed is 10 meters per second to the left. And its mass is 4 kilograms. There's another smaller object, its mass is 2 kilograms. Its speed is 5 meters per second to the right. They stick. So what I want to know is, I want to know its final velocity, or you could say speed, final, left or right. And then I want to know is, how does the energy change? So the energy of this thing changes. Well, The moment when I see the word stick, I go, this is an inelastic collision problem. So the first thing I do is P initial equals P final. So P1 initial plus P2 initial is equal to P1 final plus P2 final. One of these things is zero. Oh, actually, none of these are zero. I take it back. I'm going to plug in some values for this. This is 1, that's 2. So this is M1 V1I plus M2 V2I equals M1 V final plus M2 V final. The final velocities of those objects are the same. Why? Because they stick. It's one object. So I can rewrite this as V final M1 plus M2. And rewriting all of this, I get M1 V1I plus M2 V2I over M1 plus M2 is V final. And so that's the final velocity. One of the things that I intentionally did is I used speed and direction. These types of problems use velocity. You must pay attention to them. Velocity of 1 is positive 5. It's going to the right. So its speed is 5 meters per second to the right. The velocity of 2 is negative 10 meters per second. Its velocity is in the negative direction. So it's 10 meters per second. Negative 10. So plugging all this stuff in, 2 times 5 plus 4 times negative 10 all over 2 plus 4. 10 minus 40 is minus 30. Minus 30 divided by 6 is minus 5 meters per second. So the final velocity is negative 5 meters per second. You could either say the final speed is 5 meters per second to the left, and that would give you the answer. One of the things that I give the elastic collision problem, and then I say, now do an inelastic collision problem, and they do it, and then they're like, it's so easy. And I go, yes, I understand. That's why we don't do the other one. All you do is conserve momentum. Now let's take a look at the energy, because if you're still not convinced that I think energy is conserved in this, well, technically in the grand universe, energy cannot be created or destroyed, it can merely be transferred, then fine, yes. Some of the TAs try to get snarky, and when they go conservation of energy, they really mean on a grand universal scale. What they're really trying to catch you into a trap. Technically, that lab is conservation of mechanical energy, not conservation of energy. So it can be that mechanical energy is not conserved. Let's look at the beginning. The energy initial is just 1/2 M1 V1 initial squared plus 1/2 M2 V initial or V2 initial squared. So this becomes 1/2 2 5 squared plus 1/2 4 10 squared. So this becomes 25 plus 200 or 225. 75 joules. That's the energy that it had initially. Now the energy final, since they're stuck, is 1/2 m1 plus m2 v final squared. So this becomes 1/2 2 plus 4 5 squared. 5 squared is 25, 2 plus 4 is 6, divided by 3, or I'm sorry, by 2 is 3. So 3 times 25, or 75 joules. So you can say that energy final divided by energy initial is 75 divided by 225. Or the fraction is 1/3. So only 1/3 of the energy in the system remains in the motion of the system. Well, where did it all go? Deformation of the objects so that they stick together. Sound, heat, stuff like that. So that definitely shows that the energy of the system is not conserved. If you try to conserve energy on a problem like this, it'll just mess up. And tears and ashes and all that stuff. So that, yes?
Is potential energy included in the initial energy?
Well, what I'm really considering is I'm comparing the energy initial to the energy final. Now, what do we know about those objects? It remains on a level surface. So if it remains on a level surface, I don't care. So we did a collision. Let me take a look at the problem set and see if we're ready to. Okay, we're good on most everything. One last thing that I want to cover. Another conservation of momentum and energy thing. Oh, this will be definitely a good problem to do. Oh, I know exactly what I need to do. One of the things that I like to do in class is talk about the lab experiments and in fact do them, just like I did the two-dimensional motion problem. In, I think it's the Monday lab, you're going to do conservation of momentum and conservation of energy. And in this particular problem, you have that cannon that you use for 2D motion, and you're going to put that steel ball on it, and you notice that your launcher also has an arm. So you fire the ball, you don't know what its velocity is, but you do know that the mass of the ball is some value. And you work with, you determine the mass of the arm. So this is it's a metallic construct, but there's like a little basket at the end of the arm. The ball enters the basket, it sticks, it stays inside. It moves with the ball inside in this particular direction. And then at an angle, theta, this final velocity is equal to 0. So explaining the motion again. You have an arm that's basically, it has a basket at the end of the arm. You fire a ball into it at an unknown velocity. You know the mass of the ball, you know the mass of the arm. the ball and the arm lift to a particular angle. The question is, given that angle and all these masses, what is the velocity of the ball that you fired? So what we're going to do is we're going to start at this end and work backwards. From here to there, so we have 3 states. One is the moment before impact. The ball is about to hit the arm. B is the moment after impact. And C, the arm is stationary. A to B is an inelastic collision. If you go from A to B, you cannot conserve energy, but you can conserve momentum. B to C is motion with no friction. So from B to C, in this particular case, momentum A is equal to momentum B, but energy A is not equal to energy B. From B to C, it's a motion, so energy B is equal to energy C. So in this problem, there are 2 mini problems. 1, conservation of momentum from A to B. 2, conservation of energy from B to C. Let's think about from B to C, because that is an energy problem. So the ball is in there and it has a velocity v. It starts, or I'm sorry, it ends at that position right there where there is no velocity. It is a conservation of energy problem. Now remember what I told you, it doesn't matter how that motion looks like. In this case, it's kind of circular because it's at the end of the arm. But all that does matter is that height h. Because if I have that height h, I know that the mass of the arm plus the mass of the ball, GH, is equal to 1/2 mass of the ball plus mass of the arm, V squared. This is that state. This is that state. We're effectively just running backwards. Now you could measure the physical height change. I think they give you like rulers and stuff like that. But the one thing that they frequently ask for is that angle. And so we end up forming a little right triangle right there. If this length is length L, that length L is the length of the bar. That length, it has to be the same as that length because the lengths of the bars are the same. Which means that, let me get another color. Which means that this length here is L minus H. Because that length H is still that length H. And so this length here is L minus H. Now what do we know? We've got an angle. Let's solve for theta. If we have cosine theta is the adjacent side, L minus H, over the hypotenuse, which is L. You're going to measure theta on this thing. They have little angle scales. So this is L cosine theta equals L minus H, or H is L minus L cosine theta, or L 1 minus cosine theta. And so that's the height. So if you know the length of the bar and the angle, you can easily determine the length, the height. So that means that M2 plus M1 GH is M2 plus M1 GL 1 minus cosine theta. And that is equal to 1/2 M1 plus M2 V squared. Now there's an M1 plus M2 term in both, so they cancel, and I'm left with GL 1 minus cosine theta is equal to V squared over 2. Or 2GL 1 minus cosine theta is equal to V squared, or 2GL 1 minus cosine theta is equal to V. And so that is the velocity. If you know that angle and the length of the bar coupled with gravity, you can determine the velocity of that ball at the bottom. It's the same thing as you could either push an object with a particular velocity, sort of like a swing. The kid is the ball. The swing is the arm mass. You push it, the kid reaches a particular height, and you can measure the angle at which it comes to a stop. Now, if you push it with 5 meters per second velocity, and it goes up to a height, stops, and comes back down, it will come at you with a velocity of 5 meters per second. So we're allowed to work forwards and backwards through this part in order to get the answer. So if we start at a particular theta with a particular arm length, we can get a velocity from it. Now the last bit, we got to work from B to A. B to A is an inelastic collision. So PA is equal to PB. Momentum A, the only object that's moving, and let me label, I'm going to say this V is V sub B, and that V is V sub A. The momentum at B is M1 plus M2 VB. I'm looking for VA. I'm looking for the velocity of the ball that the thing fires. This is what you have to do in lab. The VA is M1 plus M2 over M1 VB, which means that this is M1 plus M2 over M1 square root of 2GL 1 minus cosine theta. And so we have VA. So now we have one expression. The velocity of the ball is a function of mass 1, mass 2, gravity, the length of the bar, and theta. So it doesn't matter what numbers I give you, you can just plug it in and get it yourself. Once again, this is one of the advantages of doing it in alphabet soup mode, where you write out all the letters. One of the things that we can ask ourselves is, do I believe this equation? Is it of the right form? If I do a unit check on this equation and I get meters per second, I have confidence in it. So mass is kilograms. Mass is kilograms. Square root. Numbers don't count. G is meters per second squared. L is in meters. 1 minus cosine theta. All of them are numbers, so they don't matter. I'm left with the square root of meters squared over second squared, which gives me meters per second. so the units do check. This is one of the major advantages of alphabet soup mode over plug and chug, because you can double check your units. I've double checked, I feel very confident in it. The other thing is, and we're gonna wrap this up, we'll wrap up 5 minutes early. But the last thing that I really wanna make a point about is when you plug and chug and you do 8 different calculations, you are introducing 8 different opportunities to make a mistake. The other thing that you're doing with plugging and chugging is you're rounding. Rounding is bad. Why? Now, for the most part, it isn't. But if you're doing 8 different calculations where you're rounding by 5 to 10% at a whack, eventually you're gonna get bit rot and information will start to diverge from the true answer. Doing this one calculation, you get the most accurate answer. And so it is my humble plea for you guys to give up your hurtful and hateful ways and embrace alphabet soup. That's it. I'll see you tomorrow.